Hey, why don't we start? This is Glenn Letter, who's been very active in modeling and had a great presence with the COVID page and data analysis and developed a following. In the original program, his talk was attributed to two different people, the title that is, and I corrected that. But at any rate, he's going to talk about problem sets, and he's published several books. And this is on modeling for epidemiology and ecology. Glenn, take it away.
Thank you, Brian. So I'm going to talk about what I call linked problem sets. You could think of them as being projects distributed across a variety of sections. So this book should be out in approximately April. It was written as both a textbook for an undergraduate course and a source of problems and methods to supplement DE and modeling courses. Among the characteristics of the book, it features 50 sets of what I call linked problems. These are multiple problems on a single model distributed over multiple sections. All the problems in the book are accessible to students taking a first course in ODEs. And so in this talk, I'm going to look deeply at two of the sets. And I also have a special bonus. I am going to propose an improvement to the Turing test. So the first model I'm going to talk about that's going to take up most of my time is a plankton food web model. This model appears in 4 sections. It's introduced in a mechanistic modeling section on scaling, and then it appears heavily in the chapter on dynamical systems analysis. I've grayed out section 6.2 because there's nothing that is not routine in the material in that section, and I only have so much time for this talk. I can envision breaking the 4 problems up into a total of 11 parts, and I'll show you the parts that are not from section 6.2. So first, let me give you an overview of this model. The model components are 3. There's free nitrogen, there's phytoplankton, and zooplankton. And so it's a food web because the free nitrogen is a resource for the phytoplankton, which in turn is prey for the zooplankton. What's interesting is that when the phytoplankton and zooplankton die, their N content immediately re-enters the free nitrogen pool. The zooplankton equation you'll see is the standard predator equation used in the Lotka-Volterra model. The phytoplankton equation has free nitrogen uptake and natural death instead of Lotka-Volterra's natural growth. And please note my footnote. And total nitrogen is conserved, so we'll be able to eliminate the F equation, leaving a modified predator-prey model. So here's the first part of the linked problem set. Problem 3.6.12a gives a narrative that explains what I just said, and it gives students 4 mechanisms of nitrogen transfer. 2 of these are straight transitions associated with death. And 2 of them are like predator-prey terms. One's consumer resource and the other's predator-prey. And so all the students have to do in this part is write down the differential equations, and here they are. This will come up in the next part. So just notice if you add all of these together, the right-hand side is 0. Okay, so the next part, I've grayed out part B because I've just mentioned it and don't need to write anything more down. And then the next part is to use this result to eliminate F from the P equation. So here's the P equation. And so if I replace F with N minus P minus Z, I get this, and I can do some algebra to clean it up. And I end up with an equation that looks sort of like the logistic growth equation with a predation term. So here's the logistic growth part, and then there's a predation term here. Next part of the problem, still problem 3.6.12, is to non-dimensionalize these equations using reference quantities that I've given. And so the best way to think about non-dimensionalization is simply doing a substitution. So any place where you see d by d time, replace it with c times n times d by d dimensionless time. Every place where you see c plus d times z, replace it with cn times z. And if you do that systematically to the P equation, you get the second equation that's listed here. And notice that there is a common factor of C everywhere, so except for the A term, and there are two common factors of N everywhere except for the A term. So when I divide by Cn squared, I'm going to get all dimensionless things, including the dimensionless grouping A over Cn, which has emerged from the scaling, and I'm going to call that alpha. So we just need to briefly remember that alpha is A over Cn. And similarly, I get the other equation. Okay, next part of the problem is to explain the biological significance of the parameters alpha and beta. So this is modeling more than its differential equations. I think modeling, differential equations are a component of modeling, and I think differential equations courses should be teaching modeling. And so part of modeling is understanding what the parameters do. So to explain the significance of the parameter alpha, look at this chain of reasoning. F is a subset of N, so it's less than N. And that means that CNP is bigger than CFP. Alpha, we remember from last time, was A over Cn. And if I multiply top and bottom by factors of P, I get AP over CNP. And then if I use this result, I get that that's less than or equal to AP over CFP, which is important because those are the two terms that are in the P equation when there isn't any zooplankton. So that means that alpha is the lower bound of the ratio of P loss from death to P gain from consumption. So large alpha is bad for the phytoplankton. And similarly, beta is the lower bound of the same ratio for zooplankton, and large beta is bad for Z, but it's also bad for P because if no, I think I said it the wrong way. I made a mistake there. Large alpha is bad for P. It's also bad for Z. So there's a mistake in that, and I'll fix it before I post my slides. So there's some special advantages of linked problems, and one of those is you can give students the full answer to one part before they do to the next part, and still treat the linked problems as a project by having them do a final report. So in this last problem, there's a much stronger statement we can make about the significance of alpha and beta. So here's what we had before for alpha and beta, but notice what else we can do with this. Suppose alpha is greater than 1. So that means 1 is less than alpha, which is less than or equal to AP over CFP. And so that means that CFP is less than AP. So P cannot persist. So alpha greater than 1 is alpha less than 1 is a requirement for the existence of P. It's sort of like a basic reproduction number for P. And similarly, beta greater than 1 means that Z can't persist. And so we can plot this graph in the parameter space that shows that when alpha is bigger than 1, you get no P and no Z. And when alpha is less than 1, whether you get Z or not depends on the value of beta. Next, and now we're moving to the next chapter, we're starting to do dynamical system analysis. So let's determine the equilibria for this plankton model, being careful to indicate any restrictions on existence. This is pretty routine, except that students have trouble with dividing problems into cases. So one way to do that is to have them look for specific cases. Can you have an extinction equilibrium in which both P and Z are 0? Yes. Can you have a Z equilibrium in which P is 0? No, because if P is 0, then Z has to be 0 for the second equation. A P equilibrium would require Z equal to 0 and P positive, and if you track that through, you get a result for P and a restriction on the value of alpha. And similarly, the PZ equilibrium has both of the quantities positive, and if you track that through, then you solve this linear system of equations and you get the values for P and Z, and that shows that this only works if alpha plus beta is less than 1. Next, still in section 6.1, we'll sketch null-Klein plots. And I know people have different backgrounds here. It's possible that some of you have taught from old-fashioned differential equation books that don't have null-Kleins. So I'm going to put several minutes into talking about the null-Klein plots. The use of color, which is new in textbooks, make null-Klein plots really easier to understand. So Z null-Kleins are when Z prime is 0. There are 2 of these. And in my plots for each of the 3 cases, I've plotted red lines for the null lines. So P equals beta is plotted in red. And what that red null line tells me is two things. One is it tells me that direction arrows for points on that null line are going to have to be horizontal because Z is not changing. And on one side of that null line, Z is increasing, and on the other side, it's decreasing. And this is the same for each of the three cases, which is why I did the Z null lines first. The P null lines are more complicated because one of them is an equation, Z plus P equals 1 minus alpha. If alpha is bigger than 1, that equation lies outside the first quadrant, so we don't see it. And as alpha and beta change, this we're keeping beta fixed. As alpha decreases, this null line moves upward. So let's look at the middle one. If you're on the null line, then that means P is not changing, but Z is. If you're above the null line, P is decreasing, and if you're below it, Z is increasing. This is what you can learn from each set of null lines looked at individually. The real power comes when you combine them together, and then you get this full null line picture. And so in each of the regions, the combination of up arrows, up and down arrows, and left and right arrows restricts the direction of motion to one quadrant of the 360-degree space. All right, so there's our null line plots. And now let's draw some conclusions from them. So I've just repeated the null line plots here, and I'll start adding conclusions. So I've drawn circles around stable equilibria. And we know these are stable equilibria because they are attractors in a no egress region. So if you look at this first picture, in the left region, you can't get out of that region. There are no arrows that lead you out of that region. If you're in that region, you have to go to the left and down. So you are required to go to that origin. So that makes that a stable equilibrium point. Same thing for this one. The squares are unstable because they are repellers in some region. So if you're in this region here, you cannot get to that 0, 0 equilibrium because you're forced to move to the right. And this is a good example to look at, which is why I picked it for this talk, because the coexistence equilibrium for the most complicated case cannot be determined from null lines. It looks like we could be circling around. We could be spiraling in or we could be spiraling out, and we won't know the answer until we do an analytical method, which is what we're going to do next. So I skipped a couple of parts. I'm on to the last section. And so this time I'm going to use the Routh-Hurwitz conditions, and I'm not going to spend a lot of time on this because my second problem has a better illustration of Routh-Hurwitz conditions. So for two-dimensional, we just get that you're asymptotically stable if the trace is negative and the determinant is positive. That occurs here. The thing that's important to notice is that I have not solved these equations for P and Z and plugged in the formulas. I don't need to do that because the trace is minus P. That has to be negative. The determinant is delta PZ. That has to be positive. So the PZ equilibrium is stable whenever it exists. So we get information here that we didn't get from the null lines. Lastly, let's explain the predictions that the model makes. So here is the parameter space again. So alpha and or beta increasing decreases the viability of zooplankton, and larger alpha can make the whole system go extinct. Comparing that with the standard predator-prey model, which is logistic Lotka-Volterra, there is no alpha in that model. So this graph is essentially what you see when alpha is 0. So this model that we're looking at is slightly richer than the logistic Lotka-Volterra. And now let's add in the regular Lotka-Volterra. And this model has results that are ridiculous. If beta is larger than 1, then the phytoplankton population goes to infinity. If beta is less than 1, then you get a semi-stable equilibrium point, which is not a good example of oscillatory solutions. Real oscillatory solutions are stable limit cycles. Which brings me to the Turing test. So the Turing test is intended to determine whether a machine has achieved intelligence. So the idea is that if a machine can carry on a conversation and you don't identify it as a machine, that counts as intelligence. Clearly, we're close to passing that test, but AI has not achieved intelligence. So I'm going to propose a new test. Train the AI by feeding it lots of writings in biology and mathematical biology, but only ones that don't mention the Lotka-Volterra model. and then ask it to explain why the Lotka-Volterra model is bad. And if a machine can do that, then I will call it intelligent. Now we'll go on to my, Brian's clapping. Every time I give a talk on predator-prey models, I try to find a new way to disparage the Lotka-Volterra model. For the rest of my talk, I'm going to look at an epidemic model, an SIR model with loss of immunity. So I'm going to add loss of immunity to a 3D model that's in the book text for an SIR disease that has the usual features, but also a disease-induced mortality. This model appears in 3 sections, and again, I'm going to skip the part that uses eigenvalues. So here's the base model. I have an SIR model. I have a constant birth rate. I have natural death, and I have a special disease-induced death term. And this is what the results look like. If you look on a short time scale, you see a spike that would happen if you didn't have the birth and death. This is what the model would look like for all time if you didn't have the birth and death. Because you've added the birth and death, you get this version, which you don't see if you only do equilibrium analysis. In order to see this version, you have to do simulations. And what you discover is that after the initial epidemic is over, the susceptible population gradually increases because new people are born and the disease is kept at bay. Eventually, the susceptible population gets large enough to trigger the next spike. So that's what happens if there is no loss of immunity. All right, now the first question we're going to ask students is to add in the problem with loss of immunity and scale it. In the interest of time, I put this slide in to show just the blue part in the S equation, but I'm not going to talk about it any more than that. Next, we modify a computer program to run 2 simulations. I'll talk a little bit about more about that in a minute. And then we compare the results. So the plot on the left is with no loss of immunity. The plot in the middle is when loss of immunity is really slow. P equals 1/2 means that on the average, most people don't ever lose immunity, but some do. And phi equal to 5 means on the average, we lose immunity every few years. And so the differences are that with faster immunity loss, the cycles start sooner, they have shorter quasi periods, their amplitudes are initially larger, but they decay faster. In order for students to do these graphs, they don't need to be experts on computer programming. They just need to be able to modify the program that I have given them. So this is the program that's associated with the book and that produces the first graphs that I showed you. There's a section that defines problem parameters. You'll have to add the parameter phi to that. You may need to change the time interval. You need to change the differential equations. This one only has S and I. It doesn't have an N differential equation. So when you unpack the variables, you'll have to add a third instruction to unpack N. Then you'll add new formulas to replace these two and add a third formula to calculate the derivatives and assemble them. Students do not need to be experts in computer programming to modify these few lines that are in this function. And that's all they need to change to be able to run simulations for a different model. The last thing that we'll talk about is using the Routh-Hurwitz conditions to determine the stability of this disease equilibrium. In this disease equilibrium, it's easy to write down the formula for S. It's hard to write down the formulas for N and Y. I'm not going to write them down until I need to. So instead, I'm going to use the Routh-Hurwitz conditions in as much generality as possible. The characteristic polynomial is cubic, and I've given instructions for how to compute the coefficients, which I don't have time to talk about. And we get stability if all the coefficients are positive and C1, C2 is greater than C3. So applied to this particular problem, we get this Jacobian. Whenever I'm writing down a Jacobian, I always try to keep it as simple looking as possible. So I'm not going to plug in a formula for Y, which will make this entry messy. And if I leave this entry the way it was, I'm going to have in parentheses 1 plus phi plus by. That's messy. So I'm going to give that a name Q and just put it in as epsilon Q. I'm going to observe for later that this quantity is larger than d phi because d is less than 1. All right, so then you calculate C1, C2, C3. You can find a lower bound on C2. And when you use the lower bounds on C1 obtained from here and the lower bound on C2 here, you immediately get that C1, C2 has to be bigger than C3. And so the EDE is stable whenever it exists. This is typically what you find in epidemiology problems. There are some problems that are particularly interesting that don't always have a stable endemic disease equilibrium, but this is a fairly standard problem, albeit a little bit more complicated than the standard one. So that's it. I've hit my time without going over. You can find these linked problems and 48 other sets in my new book, which should be out in April. Again, all the problems in the book are accessible to students taking a first course in ODEs. Feel free to contact me with questions or comments. And if anyone wants to have me visit, I'm interested. I got lots of time. Brian said I'm at Nebraska. I'm an emeritus professor at Nebraska, but I'm retired now and I actually live in Denver. Denver has a great airport with, it's easy to get from here to anywhere. So with that, I'll take questions.
Well, thank you, Glenn. Any set of questions? By the way, the link to this text is in the abstract on the main page. I do have a question. You thread these through the text. That's the
Yes.
whole. And when did you start? Did you start doing that in your teaching as well, namely revisiting some things?
Yes. Yes. It's also a feature of the first edition. So this book is, it was hard to decide whether to call this a new book or a second edition. It's about 50% different from the first one. So we compromised, we gave it a new name, but we're calling it the second edition. The original one is Mathematics for the Life Sciences. And that book has some linked problems in it, but nowhere near as many as this one. That book does not have case studies. This one has many of the sections in this book are case studies, which are like linked problem sets, except they're all put together and I did the work, except for exercises that occur in them. The main reason why the book changed a lot between the first and second edition is because of COVID-19. That was the primary motivator for doing a second edition. First edition was mostly ecology with epidemiology used as problems. The second edition is mostly epidemiology in the text with lots of problems in both epidemiology and ecology.
So there's some obvious ways you can extend a problem. For example, in an ecology, you could introduce a new trophic level. So you go from a single. What are the kinds of strategies? If I'm teaching a course and maybe I'm using a standard text, but I'm trying to create these threaded problems, what other kinds of strategies do you use to link and extend?
Okay, that's a good question. So the way I would write one of these linked problem sets is I would start by envisioning an undergraduate research project. So an undergraduate research, so the plankton model that I showed would have been a great undergraduate research project. The difference is that instead of giving them all the instructions, you would just give them the original problem and say, do with it what you can, come talk to me every week and we'll see where you are and then we'll come up with new ideas for moving forward. All right, so envision what an undergraduate project would look like. An undergraduate project, not a professional research paper, because you want it to be detailed in the sense of having lots of steps, but you don't want it to be very difficult. So you envision an undergraduate research project and then break it up into parts. And as I noted earlier, the big advantage of linked problem sets is that you can make sure that everybody starts on the same page for each part, because you assign part A, give them 2 or 3 days, have them turn it in, and then you give them the answer to part A. Then they're all starting with the correct answer for part A before they move on to part B. So you don't want people doing dynamical systems analysis on a bad model. You want them to get the model right before they do the dynamical systems analysis.
Okay. Speaking of books, tomorrow we have a session at 3:30 for about 55 minutes on 4 authors. trying to answer the question of how and why they wrote a book. And maybe if you've authored a book, you might ask the question, what was I thinking when I agreed to do that? That's another question.
Absolutely.
I noticed Tom Judson is in the audience, and while he's not on that panel, he may join in with, what was he thinking when he started writing books? We all think we can do that. We've all been in a department saying, I think I could do better than the department head. And then we go, no, I don't want to do that. And we say, why did a text do that? I would have done it differently. And then we start writing and then we put it away and go, no. And some, like Glenn and the authors that are going to be joining him tomorrow, have the fortitude and foolishness to proceed.
Stubbornness is the right word.
Proceed to fulfillment. And many of these text ventures take paths just like Glenn's with this feature. And some have other features and other paths. And it's nice to hear from authors about what they thought about, look at an example, and we really appreciate your sharing that with us. So I'm going to shut this down and get ready for our keynote. And I want to thank you, Glenn, and we'll see you and your colleagues tomorrow.
Thank you.
Okay.